So why do we test in the first place? I asked on Twitter, has anyone ever run into a situation where you didn't test something that you should have tested and it blew up in your face? And so you may have had different experiences. I got no replies at all. And when I asked all my friends, they said, no, it's never happened. I just don't need to test things. And so I also started thinking about companies that have failed because of bugs that were so significant that their business failed. Also, none of them. I can't think of any of them. And I asked around, no one knows. So maybe my entire talk is pointless. But that kind of backfired in my own face, actually. So don't ask this kind of thing if you want to motivate why testing. I will give you some anecdotes. I once accidentally sent myself 2,000 emails because I didn't test something. The idea is that in some kind of web application that I made, you can have two kinds of triggers. One is send it to another service, and another is send me an email. And the logic for whether to send an email was, if I've never sent an email about this thing that I need to trigger before, then send an email. But disregard whether it's already been sent somewhere else. So I'd been using this for 2 years. I had 2,000 of these things lined up, and I started sending emails to myself for all of them. But this could have been prevented if I just written some small test. I've also seen a whole bunch of much more important things go wrong, because my day job is to find problems in other people's code. It's mostly financial institutions, people with a lot of money and very bad code. So what I want to talk about when I say why do we test is the theoretical part, not the if you don't do this, then the rockets will explode. It's really the foundation of why do we do this. So imagine this set of all possible programs that you could write. For your specific application, only a subset are the correct programs. Now, imagine if writing a program was picking a random point in this space, then it would be rather unlikely that you'd get a correct one. So in Haskell, we use a type checker because the programs that type check are a subset of all the programs, and we believe that there is a small number of programs that is correct but not type correct. So in this diagram, I've said that all correct programs are type check. Now, of the correct programs, ideally what you'd want is to have the tests in such a way that any program that is correct passes all of your tests. That's not always the case, but that would be ideal. And if in the best possible case, you could say any possible program that passes your tests is also correct. Now, this is often not the case, but I'm going to teach you how to strategically engineer your tests in such a way that you can still be confident about your code. So the point of testing is really to close in using the set of programs that pass our tests onto the correct programs set. So I'm going to now start with a part where it's for beginners, where I show how you can model this in Haskell. So I argue that there is this nice definition that I'm going to be using, that a test is just a piece of code that you run. And if the code crashes, then the test fails. If the code doesn't crash, then the test passes. So you can express that like this. There aren't actually types like this anywhere, but this gives you a nice idea. So you run a test. If it crashes, then the test fails. If it doesn't crash, the test passes. And in Haskell, we have some nice facilities to have it fail in a nice way. So these assertions that we put into our tests are essentially nice ways of making the program crash if something goes wrong. So this is a combinator called should be. And the idea is that you give an actual value that you got out of your actual code and an expected value that you want to be equal. And then this function will make the code crash if those two aren't equal, with a nice error message, with a nice diff, so you can see what went wrong. And here is an example test in Haskell. And this is where I'm going to ask you to look through the repository so you can try it out yourself. I'm going to show you later how to do that. So what you see here is a test suite. So that's some code that you run that will give you nice output about your tests. That's declared with hspec. That says, I'm now going to declare a bunch of tests. And then there's a line describe, which lets you scope the code that you're going to talk about. In this case, I'm going to talk about addition. And the next line says it, and then a sentence. And the idea that this is a sentence is very important because it requires you to describe what your code is doing what your code is supposed to be doing in your test, so that when someone else reads your test later, they can still figure out what you were trying to test. So this is supposed to be read as addition still makes sense. And that's also how you will see it in the output. And then the next line is the actual test. So that's just a piece of code that can crash. And we make it crash elegantly with this should be function, where I say that 1 plus 1, which is the actual value, should be the same as 2, which is the expected value. Now, I'm going to show you how to actually run these things on real code. Well, not real, but on our example code. So in this exercises, in this repository, under 1 testing for beginners, there are exercises. And I've written the same test here under test addition spec. So it's the same thing, except formatted a bit differently. And the way you run that is with stack test. And you can pass in test arguments where you say match addition, for example. Then it will only test the things that have addition somewhere in the substring of describe and it. And you can see that addition still makes sense. Now, to give you the real deal about how to get here, the important parts are in your package.yaml at the bottom. In the test dependencies, you write hspec. And in the test directory, you copy-paste this thing, which essentially says, go and find all the, you don't have to know what that does. I just copy-paste that every time. The idea is that all the tests that you write in this test directory are discovered if they end in something spec. Then there is one function that's taken out of it, which is spec imported. And these are put together in the test suite that is then run. So this allows you to put your test suite in different files and not have to import everything everywhere. All right, so that's the addition test. Next, I want to share an idea that I've been working on for a long time, which is the solution to the problem where people say, I don't know when to stop testing, so I just don't do any of it at all. So I argue that you can stop testing when the following is true. Any code that could have been written that passes all your tests and your type checker and is still wrong should exist with such low likelihood that you're comfortable with the situation. So this is a bit to unpack, and I probably will have to repeat it. But the idea is we don't assume that programmers are smart. We don't assume that programmers are diligent. We probably assume that they're lazy, and I'm going to use that in a moment. And the idea is that if a programmer is fallible when they're writing code, then it is fixable with more tests, but the tests are also, writing test is also potentially not correct. So keep it into account. And I talk about this likelihood that something is written. I'm going to talk about that in a moment later. And this is also assuming that programmers are lazy and not necessarily smart. Now, most programmers are mostly smart most of the time, right? But that doesn't help all of the time. And when I say some situation for, which is the case for you to be comfortable, what I mean here is that this depends on your domain. If you're writing missile software, if you're writing nuclear reactor control software, or something using pacemakers or something, you should probably be less comfortable with less tested code. But it's up to you to decide that. So it's really a trade-off between whether it's worth it or not for your domain. So this is what I meant when I talk about the likelihood for code to be written. If code is inherently complex, so if the problem domain is really difficult, it is less likely to have for a specific kind of code to be written at all. If the code is lengthy, then that specific code that is lengthy is unlikely to be written compared to all the other things of the same length. And the same thing goes for whether it's difficult to write a certain piece of code. So let's give you an example of this, and this is going to be relevant in the repository again. We're going to write code that passes tests and is still wrong, because this will give you an idea of how difficult it is to get to the point that I just mentioned in the situation where you can stop testing. So let's write a function that reverses a list, supposedly, and passes no tests, because we don't have any tests yet. So I have this example in the repository. In source reverse, I made this. And now your goal is to write code there that passes no tests and is still wrong, and be as lazy as possible about that.
So write nothing at all.
Exactly. So the way you check that your thing passes the tests, at the moment there are no tests, but what you do is match equals reverse, like so. Yeah. Oops, I made a mistake. I wrote reverse. So let's do reverse capital. Voila. So that's how you run the tests in a moment. So here are the 3 tests. So if there are no tests, you can just write reverses undefined. And that's fine. That passes your type checker, and it passes all your tests if you have no tests. And you'd be surprised how often this would happen in practice. Now let's add some actual tests. If you only have this test, that the empty list should be mapped to the empty list, if you now want to write code that passes your test and is still wrong, it's a little bit harder because undefined doesn't work anymore, but it's still rather easy. So what you can do is you can just say, make reverse the identity function, for example. That's also a single line. And notice that making the code pass these tests and while still being wrong is surprisingly easy if you have no tests. So if you have only the first 2 tests, for example, the single line implementation reverse equals ID is wrong, but it passes these 2 tests. And in fact, it is significantly easier to write the wrong code than the right code, which means that we're not done testing. And then if you add this last test as well, reverse 154 should be 451. Try and write some code that passes this test as well and is still wrong. And I'll get to that in a moment. Meanwhile, I'm having a drink. And I want to share a little trick with you. What you can do is open the file in one directory, in one window, and then you do stack test match reverse in the other window. Then it will just run the test once. But if you add file watch, this will keep watching your code while you edit it, and then rerun every time you change the code and save the file. So here I can actually see that if you implement it as the identity function, 2 of the 3 tests pass, and the last one doesn't yet.
Can you show the command again?
Sorry?
Can you show the command again?
TA is also test arguments in full if you want. Yes?
If when I run stack test, it's doing error.
It's an error.
There's some stack install that I need to run.
No, you shouldn't need to run stack install. Stack install is really a badly named thing. What's the error? Oh, you need to go into the exercises directory.
Oh, okay.
There's no stack program.
Got it.
Stack install is really just a synonym for stack build copy bins, which means build the thing and then put it on your path. So
Okay.
yes. Ships. Is it still on? I'll have to ask her in a moment. Yes.
So I didn't find the files.
It's in source and in test. Oh.
So when I tried to git cloning your stuff, it didn't work.
It didn't work.
It's just
Hold on, let me go and fix this in a moment.
50,000.
Can you check that I didn't mess this up because it fell out of my pocket?
It's green is recording.
Okay. Did you figure it out? Mm-hmm.
It's the thing.
Oh, so no. Try using the HTTPS link instead of the Git link.
So that's what I. So that's what I did. I went to the site, right? To
So go back to the. Oh right. So go to the this link, github.com/north. Like it's this link entirely.
browser.
Yeah, but without the git at in front of it.
Yeah, that's what I tried to do.
Yeah. No, just go to the link and then you can copy paste it from there.
Sorry. What should I change here?
So delete the git at. Try this.
Sure. So if you go to the files here.
Yeah. No.
Yeah, that's what I did. Even if you look at the files here, I didn't find the files.
Oh dear. This is from last year.
That's what oh.
This one is the one. Did I share the wrong link? Let me just check if I got the wrong link. No, it's the right link.
I know why it didn't work.
I also failed to clone it, so I manually got.
So if your link doesn't, if you fail to clone this project, it may be because you haven't configured SSH keys. In which case, I'm gonna. Hey?
You can just clone with HTTP if you don't have.
Yeah. So I'm gonna give you the HTTPS link as well. All right. So, did everyone manage this? Probably not yet. Sorry? Yeah, try that. It doesn't work.
No?
No. And you'll see the reason in the compile output, but have a look at the type and you'll figure out why it doesn't work. So that's a really good point, actually. I'm going to discuss that with the rest as well. So suppose you just write this. What's wrong with this before I run the compiler? You think so? Well, the error message is terrible. But so the problem is as follows. Reverse needs to work on a list of anything. And this is such that what's implicit here is that this is for all A. So not for an A, but for all A. This needs to work for any A. And not any A can be compared with 5 to be equal. So the problem is you need to write a parametric function, which means you cannot look into the type, the type of the value itself. You cannot look into the values inside the list. That's just not possible. And it's really good that this is not possible because it rules out a whole bunch of incorrect implementations that you could write. For example, this one. Now you can't write this anymore. You can only write truly parametric functions. Modulo some GHC nonsense. But so this doesn't work, but what you could do is this. Does that make sense? So you don't have to look at these to look at the values itself to make it pass your tests. You can just look at where they are in the list. And let's look at the next slide. So that's exactly what I described here. This is wrong, and it passes the tests. And now I argue that the correct implementation, which is the second one, I hope, is actually easier to write than the first implementation. And this makes me comfortable enough that the second implementation will be correct. Does that make sense? So because it's so much more difficult, given these tests, to write a wrong implementation than a correct one, I'm okay with stopping testing here. Even though I haven't written any fancy tests, it was just a few unit tests. And actually, even if you only write the third tests and leave out these two cases, if you leave out the first two cases there, and you only keep the third test, I'm still probably comfortable enough because the resulting code would be so significantly weird compared to the correct code that I'm still happy to stop testing there. So before I go on to the next example, suppose you had some combinator like this. And what this says is, if you have a piece of code that has an argument, and so a test that has an argument, and I use this function on it, then that test will be run for any argument that you could possibly give it. And then that becomes a test. Suppose you had a function like this. Now, in the current form, it's not possible ever for technical reasons. But suppose you had something like this. What could you do with it? We're going to explore that next, and that's going to be the next 4 hours as well. So here's another example. It's also in the repository, so we're going to do the same thing, try and write code that is wrong but still passes the tests. So these are the tests that I want you to get to pass for the sorting function. For a sorting function, rather. And it's also in the repository. It's under source sort. All right, I need to remove this thing again. So this for all a, just so you know, it's implicit. And if you want to make it, really write it down, you can do a language extension called explicit for alls. Like so.
Is there an advantage in using the explicit version?
If you just use explicit for all, then the only advantage is clarity. There are like 3 other extensions, I think, where this starts to become meaningful. And in that case, you have different semantics, whether you use for all or you don't use it. I'm not going to explain what the differences are right now, but if you go to the other rooms, I'm sure they will be happy to explain it. I mean, I'm happy to explain it as well, but it's just going to confuse you. It has something to do with being able to reuse this A in where blocks and have it be the same A instead of a different parametric one. All right, so here are your tests. Where are they now? Here are your tests. And now we're going to write match equals sort to run the other tests that I've written. That's not the right one, is it? There we go. Here are your 3 sorting function tests. So if I just, the reason why I give it such weird names is because it wouldn't clash with anything else. If I just say identity, then the last test fails again. Right? All right, I'm going to let you try it for a moment. How much time do I have? TA stands for test arguments, but you can write it out. Wow. Still wrong. No, look. The thing I write and the thing I edit is not the same. If I see, it says TAES, right? Now I turn it into TAST, and now it works. Damn it. Yeah, okay, of course. So identity doesn't pass your test yet. I have no way of gauging whether this is easy or not. Is it going?
Not easy.
Not easy? Okay. It's good that you tell me.
I think that setting up the whole thing is kind of similar.
I see.
Just the same as reverse, isn't it? Just that this one.
Yeah. No, that's it for now. But I'm gonna show you some property tests later. All right, how's that going? Going well? So you managed to find something like this? Yeah. Anyone got anything more complex? No, okay. So here is a correct implementation of a sorting function, I hope. This is significantly more complex, in my opinion, than the wrong implementation. And that means we're not done testing. So let's add some other tests. I'm going to start using this property function that I mentioned. So suppose I wanted to express this if you sort something twice, then it's the same as sorting it once. So for any list, I argue if you sort something twice, it should be the same as sorting it once. And now we need this argument somehow. So that means we're going to turn, that means our test now has an argument, and we can pass it in like so. And now I say this should work for any argument that you pass in. Now there are a lot of technicalities involved there, but this is almost something you can do, and I've written the code, this test that I'd mentioned right here. I'll push it as well. So what you need to do is add quick check to your dependencies. That's the property testing framework. And then you can write this kind of, also import test.quick check, and then you can write this kind of property. So I'll make a commit so that you can just pull. You don't have to write it yourself. So now if we have the same wrong implementation of the sorting function, where we say empty list equals empty list of one element is the same list of one element, and then 154 equals 145.
I just use identity for the other cases.
Yes, that's right. So that's what I did here. What you can't do is do this. And the reason is you need the same number of arguments in every case.
I meant like instead of the case or the pattern matching
Oh, you mean like this? Yeah, could do. I'm not going to do that for something that comes in a moment. So now the 3 first tests pass still, but the last one fails now. And the fun thing is, random input has been generated to pass into this this property that we mentioned, and after 4 tests, something went wrong. And this is the argument that was generated. That's how you read this. This is the argument that was generated. This is the expected value. So that means the left-hand side of the should be, that's what this was, while the right-hand side of the should be was this. And you see this nice diff that this one is in the wrong spot, and it's switched around. And indeed, if you try to run this through the function that we have the exact same problem. So now let's write code that passes this test as well, and is still wrong. And you see here that there have been 6 shrinks. I will get to that in the next hour. All right.
Can you show again how you did the check again, or was it already modeled?
So I put it in the test dependencies, and I also made a commit, so you can just pull if you want.
Oh, okay. How do I go?
If this seems a bit more difficult, that's the idea. You'll notice that the identity function is would also satisfy this property, but something that is both not the identity function and something that passes this 3rd test together will be a lot more like a sorting function already. I guess that's the idea. So one strategy that you could use, if this is to sort lists of up to 3 values correctly, and then do identity for the rest. And now you could argue. I wrote an implementation here. You could argue this is actually more complex than a real sorting algorithm. Maybe not. Maybe it is. It's up to you. But for the case of my argument, let's assume that this is actually still easier to write than a correct sorting algorithm. This may also not be correct. I just hand wrote that. I didn't test it. So let's add some more tests to that as well. At this point, you don't necessarily need to join in with trying this anymore, because it's going to be so ridiculously complex to write something that is wrong and still passes tests. So there's one more property that you may want to add, which is if you sort a list, then it becomes sorted. So I have this very naive way of checking whether a list is sorted, where I say an empty list is sorted, and a list that starts with an x and has the rest of the elements called x's, where all the elements in x's are larger than or equal to x, and the rest of the x's are also sorted. Now I say that if you sort a list, then it becomes sorted, using this kind of property test as well. Note, by the way, that in a real property test, you have to annotate this ls with the type, let's say list of int, for example, because otherwise GHC can't figure out what kind of list you're trying to generate. If you add this as well, now you don't need to tell me you don't need to write the code that passes these tests anymore, but can you tell me what goes wrong? What kind of wrong implementation you could still write that still passes these tests? Exactly. So if you sort correctly for the for lists of smaller than 3, and then return an empty list for the rest, then this passes the tests. So in the previous slides, here, if you just return empty list instead of ls, that would pass these tests. So there's only one more property that you need for a sorting algorithm, and it's that the new list is a permutation of the old list. And there are some interesting ways to do that. You can define an is permutation predicate, or you could implement another sorting algorithm and then say the output of these should be the same. There's all sorts of stuff you could do to continue testing this. But it becomes, if you have the two properties that if you sort a list, then it becomes sorted, and also if you sort a list, then the result is a permutation of the original, these two together are the full specification of what sorting means. And in that case, there is no more way to write wrong source code that still passes the test. So we're almost at the end of the hour, so I'm also almost at the end of my slides. So some small overview of this hour. Tests are cool. Remember the diagram. I argue that they're useful, and I'm trying to stick with that. Tests are not so complex. It's a lot less complex than the kind of monad transformer, whatever the hell, you can find in the other talks. It's just some code that you run. If it passes, then if it doesn't crash, then it passes. If it does crash, then it doesn't pass. And this is the kind of format that you use for tests. And there's one more thing I want to explain there. This spec type is something complex, and it's a writer transformer over whatever else. The idea is that you can use do block notation to write your tests, and I'm going to show you how that works before the end of the hour as well. So you can see here that you describe and then do. So that means I'm going to write multiple tests. You can also nest these describes